Hi guys, welcome back. So we want to keep discussing the processes going on in the fuel. So besides thermal processes, there are other important things going on in the fuel. Now firstly, during fission, we have a U-235 atom or U-235 nucleus that was split into two other smaller nuclei. Sometimes they call it fission fragments. I'll just use FF to denote that. FF is fission fragment. Okay. Uranium in the form of uranium oxide is being used up. So this is being used up to form a variety of fission fragments, or when they decay and stabilize, they call it a fission product. So these fission fragments, they are very radioactive. They have lots of excess neutrons. So they will, radiate out their neutrons, and then they will form fission products. Now, since we are talking chemistry here, this uranium is consumed, and suddenly what happens? Oxygen is still remaining inside the fuel, and depending on what these nuclei are, there may or may not, there may be oxygen excess or oxygen deficit inside the fuel. Okay, so the uranium is completely gone, and then you have few atoms that subsequently decay, and then there's oxygen. Depending on what these atoms are, they are accessed. Okay, so what do these fission fragments, what do? We should know that firstly they have 80 to 100 MeV each. They are going very fast. So this is called a swift ion for the reason that they are very fast. Okay, swift ions. So this is what first happens. Swift ions. So you can imagine they are going to cause the pKa cascade and ionization. So they will probably do some electronic stopping first before they start to cause the pKa cascade, if you follow the kinchin-pease assumptions. But of course, in reality, there are a mixture of both happening during the ionization phase. And during the ionization phase, they are moving so fast and they are making so many ions at the same time that they can cause localized melt and Coulomb explosions. So let's put this down: localized melt and Coulomb explosion. So what do I mean by localized melts and Coulomb explosion? So let's say you have this fission fragment going in at 80 MeV. Now most neutrons, they come in at 1 MeV. Now this fella is going in at 80. So you can imagine it's really, really fast. So it's going into a lattice of uranium oxide. Okay, it's not exactly arranged like that. Uranium oxide has a fluoride or calcium fluoride structure. So I'm not drawing it exactly to scale, but this is the structure you should be looking out for if you're wanting to look at uranium oxide. So structure of fluoride. So what it does, what this swift ion does, is that when it flies through and ionizes it, it strips off electrons across all these ions, across all these atoms. And what happens? A lot of positive charges are being placed very close to each other because this is going so fast. And suddenly, this positive charge wants to repel. And this is called Coulomb explosion. Coulomb because it's charged particles. Explosion because, okay, no explanation needed. So what happens in a localized melt? Well, you can think of it this way. If that same Okay, if this same localized area is surrounded by all its electrons, yep, it's surrounded by all its electrons, the electrons can recombine with the ions and release energy. And when it releases enough energy, these few atoms will gain a lot of kinetic energy, meaning to say that the localized temperature is very high after the recombination process. Excuse me. So after the recombination process, the temperature is very high. So if the temperatures are high enough, they can melt locally. So let's say you have a lattice here. You have this effect maybe occurring in this part of the lattice, which I shade. So this local part is melted. So that is why it's called localized melts. Okay. So how do they eventually come to a stop? You have to remember the beta formula, beta Bohr formula. Formula discussed earlier. So this is describing electronic stopping. Okay. And after that, they begin to cause pKa's more frequently. And that's we have discussed as well. It's the same idea inside uranium oxide. Except that since now they are charged particles, when they knock off pKa, you have to consider that if there's a uranium being knocked off, some of the oxygens will follow as well. Eventually anyway. It may or may not follow perfectly, but if there's a mass migration of positive charge uranium, positively charged uranium 4 plus ions, because this is uranium 4 plus, 2 minus, 2 minus, so you have something like that. If many of these uranium 4 plus are migrating to the right, for example, you can be sure these oxide ions are going to migrate as well, and they're going to follow. Okay, so after this it has lost most of its energy. This fission fragment is going to be lodged into the fuel lattice. And depending on their half-life, they'll either quickly decay or slowly decay and release their radiation. It can be a neutron radiation, it can be a beta radiation, it can be whatever radiation it's there. It will just try and stabilize itself. But once it radiates all the neutrons and everything, it just becomes a fission product. And how does this affect the chemistry of the fuel? Well, the elements they actually change during decay. So the elements actually change during decay. So uranium-235 splits into 2 smaller nuclei, which are of a certain element, and when it changes during beta decay or alpha decay, it will become the fission product that is more stable. And depending on the chemistry of this fission product, the chemistry of the fuel will change. So what chemical groups can this fission product be? And what can they do? So what can a fission product do chemically to the fuel? Of course, to the fuel. Now it depends on their group, alright? It depends on their group in the periodic table. Alright, so it depends on the group in the periodic table. Okay, so let's just do the simplest kind. We have noble gas. So what kind of noble gas are usually formed during fission? Well, if this is splitting in two, we will have atomic weights of about 100, plus minus 100. Okay? And in fact, there is a certain fission yield that looks something like a M shape. Now this M shape is if we have a yield versus a atomic mass, we'll have a peak here at about 140 and another peak here at about 90. Why this is so? That's a nuclear physics kind of a thing. It's because of the shell model. If you know what the shell model is, if you're not sure, don't worry about it. Just know that the fission products, they are distributed in this kind of a manner. So if you talk about noble gases, only two of them kind of come out of this curve. It's either xenon or krypton. They're pretty long term. So if this fission product is a xenon or krypton, what will you do? Well, these noble gases, they tend to be embedded in the fuel, and where do they go? They'll go near to the voids or the surfaces. So these guys will try and find voids in the fuel or vacancies, and they will tend to want to sit there. So they will migrate. Okay, and now the other thing is that if we consider this reaction, so we have some O2 plus 2 oxygen, and then we have krypton plus something else. Okay, we have kryptons plus something else. What just happened to the density change over here? This is a solid, 10.97 gram per cm cube, thereabout. Krypton, this is way less than 1 gram per cm cube. So in effect, this actually has caused the fuel to expand. Overall. So the fuel has expanded, it's releasing gas, and when it releases gas, the fuel itself will begin to expand or swell. So this is the other swelling mechanism. This time is due to fission gas production. So the swelling we have mentioned before, that was due to the neutron damage and the creation of Frankel pairs. And well, there are voids that are stable inside the fuel or the metal, and then the interstitials will migrate towards the grain boundary or towards free surface. The overall effect is that the fuel or the metal actually swells. Now that is due to Frankel pair creation. This swelling is different is because there are fission products being made and they are in gas form. That's why the fuel swells. So this gas is so-called trapped in the fuel, and that causes the fuel to be so-called more porous and expand. Excuse me. So it can be krypton or xenon here, but the effect is more or less the same. The fission, these gases will exert pressure on the fuel pellet and cause it to expand. So creation of such species tend to decrease the thermal conductivity of the fuel, since when the uranium is gone, it's replaced by a gas which has rather poor thermal conductivity. Furthermore, since oxygen from the uranium oxide is now free, it can go and react with some other metals nearby. For example, if you have a fuel here and you have a cladding here, zirconium and iron will be here. If there's enough oxygen being created in this process, it will start to eat into the cladding. It will start to oxidize the cladding. Now that's a bit of a troublesome thing. So the cladding will become more brittle over time due to this interaction. So if you're talking about chemistry, these are the noble gases that are being made. Of course, helium is a noble gas as well. Helium is a noble gas. It is formed via alpha decay. And if these fuels are near the cladding, these noble gases can be inserted into the cladding as well. For example, helium. Or if the fission reaction is happening here, the xenon and krypton can also be inserted into the cladding, and that causes it to become more brittle. So this is especially a problem in the case of helium, and there are entire research topics that are talking about helium embrittlement. This is a very important aspect of nuclear materials. Okay, and in fact, fission gas behavior and bubble behavior, gas bubbles. So fission gas and gas bubble, because when the gas collects in the voids, they become bubbles. So this is quite an extensive study in itself, and I'll leave it to future videos. Alright, now we are done with group 8, or some people call it group 18. Okay, let's move on to group 7. These are halogen. Again, we are talking about heavier halogens because of the fission yield. So we're talking about iodine plus bromine, but iodine is the more important one. Why? Again, it's because of the fission yield. So iodine is very interesting because it can react reversibly with metals at this temperature. So let's say you have a metal plus iodine. Okay, so you have some iodine here. So the metal and iodine will combine. Okay, so M is a metal atom. So this is a Z number of iodine atoms, and it will form a metal iodide of some form. Now these are pretty volatile, and in a reactor, this can, in fuel, these are pretty mobile. So what can happen? This reaction can occur at the sides of the fuel where the temperature is lower temp. But then it migrates to the center, and this is hot. And when this is hot, the reaction actually reverses. Okay, so this is reaction 1, this is reaction 2. So 1 happens on the outside, 2 happens on the inside. So what we have is MiX going towards here and iodine coming out. So the metals are out here, for example the cladding. So the metals are outside, they react with the iodine. The metal iodide goes to the center and deposits the metal in the center. So this can cause a very interesting effect. So metal is effectively being transported from the outside, especially if the fuel is touching the cladding. It's transported from the outside into the inside. So this kind of corrodes the cladding, and this causes the migration of the metal. So this is what a halogen can do. So that's the chemistry that's going on there. Now let's move on to other elements. Next most straightforward is group 1, the alkali metals. Now, the most important one you're talking about is cesium. Now, cesium is formed very often in nuclear fission, and as we know, since there's oxygen free in the reaction and cesium is hanging around, the most common thing that cesium will form is this cesium oxide. Okay, if there's water, then the hydroxide will form. If there's any steam around, the hydroxide will form. And we know that this oxide is very different from the chemistry of uranium oxide. So UO2 and cesium oxide, these are very different oxides. So this tends to form a different phase. How do we know these oxides are different? Now this one can dissolve in water, this one cannot. Okay, that's one way of telling that they are chemically very different. So cesium, or the oxides of cesium, do not mix. They do not dissolve in the UO2 and the same phase. On the other hand, we do have oxides that can dissolve in UO2. And how do we determine which oxides, or how can we see which oxides are dissolvable? We can look at this thing called a Ellingham diagram. That's a thermodynamic way of viewing the things. So if we have similar Gibbs free energy, we will have similar phase. Okay, so that's a very simplistic way of putting it. There should be more discussion, but I'll just leave it as that for now. But the idea is behind why they mix and why they don't mix is always the Gibbs free energy. Okay, so I'm not going to elaborate on this. This is a very skimmish, very poor way of discussing this, but that's just an introduction, just to let you know these kind of things exist. So we do have oxides that can dissolve in the uranium oxide. So which oxides are soluble in the uranium oxide? Well, where is uranium located? So we draw the periodic table. We have the group 1, we have group 2, we have the lanthanides and the actinides. And the actinides. And over here we have all the transition metals. Okay, and here we have start to have all the groups here, and the last two here are halogen, noble gas. Then here are the amorphous and everything. So this is group 1, this is group 2. Okay, where is uranium? Uranium is over here. So the uranium oxides, which oxides are soluble in uranium oxides? Well, obviously, well, not say obviously, but logically speaking, there will be elements all located around the same area of the periodic table. So lanthanides and actinides, they are usually dissolvable in uranium oxide. So for example, you have plutonium oxide, and you have the rare earths as well. These all will be dissolvable in uranium oxide. Where does plutonium come from, you may ask? Remember, we have uranium-238. When it goes through an N-gamma reaction, when it captures a neutron, after a few decays, Okay, it should get uranium-239 first. After a few decays, it becomes plutonium-239, and that's where the plutonium comes from. So in this lanthanide, actinide phase, you have uranium, you have plutonium, you have rare earths as well. Things like neodymium. So neodymium, all will be found here inside this uranium oxide phase. And sometimes a limited amount of molybdenum and zirconium will dissolve here as well. They have limited solubility. And it depends on their oxidation state as well. But as you can see in the periodic table, neodymium is in the lanthanides, uranium is in the actinides. That's why they like to dissolve in each other. Now the other extreme is that no oxides are formed at all. No oxide form. So what metals like to exhibit this kind of behavior? These are the noble metals. So these are found in this region, near the transition metal region, but these are where the noble metals are. What are these noble metals? Well, in this case, they're not gold, because gold is a noble metal, but it's not really formed so much in the uranium fission reaction. The more important ones are ruthenium, technetium, rhodium, palladium. All these are noble metals. They will form metals inside the fuel pellet. These guys prefer to exist as metals. So yes, it can oxidize, but it tends to try and stay on its own. And sometimes molybdenum is also included here, because molybdenum is like not that reactive, but reactive enough to get oxidized sometimes. So you'll find some molybdenum here, and you'll find some molybdenum in the lanthanide and actinide phase. So molybdenum is somewhere in the middle there in terms of chemistry. Now what about group 2? We haven't talked about this, but group 2 is similar to group 1 and is kind of special in its own. These are called the alkaline earth oxides. So they will form another phase. Okay, they will form another phase inside the fuel. Okay. So in summary, what are the groups that we can look at? What are the important chemical groups? Important chemical groups in fuel. Now you have the group 1, which is the cesium, group 2, and these will form oxides of different phases. So you have the group 1 oxides, cesium oxides, and sometimes they will form the complex. This is what they will react with the uranium oxides to form this element. Oh no, not this compound, sorry. The group 2 oxides, they will form something like this. Okay, so sometimes strontium is also included in this, the strontium oxides will be included in this group 2 oxides. You have the lanthanides and actinide groups. So if you have to look at the periodic table, the rough shape of it anyway, you have the group 1, you have the group 2, you have the lanthanides and the actinides. Then you have the noble metals, then you have halogens, and you have noble gas. So these are the uranium, the neodymium, the plutonium, etc. These are dissolved in UO2. Okay, next you have noble metals. They'll form metallic inclusion. Halogens, which mostly they're forming iodine is the concerning one. Noble gases. Xenon and krypton. Well, helium you can kind of include it here as well, but they don't behave exactly the same way as this xenon and krypton, even though they are noble gases. For more detailed information, you can read chapter 11 of Professor Olander's book. Okay, I'll put the link below. They can you can elaborate more on what these groups are and what phases, more importantly, what phases these groups are in. So each of these groups, usually they will kind of form its own phase, and they'll have specific behaviors based on the phase of the groups. Okay, so the gases will be forming one phase, these halogens will be another, then you have cesium and rubidium in this group 1 phase. They'll, especially this group 1, they tend to vaporize sometimes. So these, okay, let's have, so we have gases, so we have noble gas, and then we have iodine, and sometimes the beryllium as well. They tend to be in a gaseous state, especially under that high temperature. So remember, it can migrate around pretty freely. Okay. Next thing is cesium and rubidium. These are the group 1. And inside the center, these guys will be gas in the center, or they call it vapor, but towards the outside is cooler, so they have solid. On the outside, these guys will be solid, on the inside is vapor. Then you have the metallic inclusion group. So these are mostly made of noble metals. Okay, so you have the group 2, which they'll call, you have the alkaline earth oxide phase. And then you have lanthanides and actinides. So they have the yttrium, rare earth, uranium, plutonium. These all will form one phase. Then zirconium, where do you find it? Zirconium, you can find it sometimes here, because you have this kind of things happening. Or you can also find, excuse me, you can find it here as well. Okay, you can find zirconium here and here. Why? These ones are, you know, kind of in between again. And molybdenum, you can find it here, and you can also find it inside the fuel matrix. Okay, because it's somewhere in between these two. So that's all I have for you in discussing fuel chemistry. Thanks for watching. I hope you've enjoyed this video. Thank you.